Abelian combination, okay? Let's start with a buck converter, famous buck converter, okay? Very simple, inductor, transistor, and diode. Problem, how to insert, of course this is part of another thing, how to insert AC isolation transformer by using additional switches. One thing I wanted to do is make a buck gain function with a Cuk type transformer, and that's what it does, okay? So what I do here, I go to the next step, and put a capacitor here, and you see capacitor is being charged, inductor is increasing, voltage is increasing on capacitor with this current, and then next step is if I turn this switch off, what happens? Well, there is no place for there is no place for current to go, so you couldn't do this switch and this switch put over here, right? So you need another switch here, because mainly what capacitor needs, it has to be charged and discharged. So now I'm giving him a discharge path with another switch. Now you say, why are you doing so crazy thing, Dr. Cuk? Well, because I have obviously want to have two complementary switches on input, which be rated as input voltage, not, right? And then if I somehow can split this capacitance like in a Cuk converter into two capacitors, voila, here's my isolated Cuk Buck, right? And has a sound characteristic D times something and no input inductor, right? Okay, but this won't work because, why? Because when I discharge it, it's going to be, chaotic discharge. Because in this loop, you know when you short capacitance, what happens? You have 100 volts on it, you short capacitor, have you seen it? You know, and then there is all kinds of current because capacitor says, I want to be discharged. You know, give me the shortest possible time. You know, physics, right? But we can prevent that discharge, which is of course bad because when you multiply with the frequency, this is all the losses. Let's put a famous resonant inductor someplace. Where can we put it? Well, it's here. What is the next one? I think. This one here. Yeah, it shows. So next one is this here. Well, if I put a resonant inductor, I can put it in a series with a diode. This is the concept, which in the past we did put additional switches and additional resonant inductor with it. And I think that my next one, I hope that my next one shows that. Well, if you have here, if I put this resonant inductor, this is a loop, right? Let me discuss that. In this loop, I could put a resonant inductor here, here, and here. Agree? If I put it in this is active switch. That's no. Because active switch, you know, I have to make sure that the current through that resonant inductor is 0 before I can turn it off. If I turn it off before that, switch will explode. We'll have a big voltage and kill the switch on the voltage stress, right? But is any problem having a diode in series with the inductor? That's the key of my new line of converters and switching methods and so on. There's no problem because the diode says, hey, I'm conducting still current, then don't bother me, right? Okay? So there is no problem having a diode here. Okay? Now, there is a problem having diode here in the active switch, but is any problem having diode in series with a capacitor? Not really, because this is a leakage inductance of 200 nanohenry, and this is 5 millihenry inductance. I mean, who cares, right? So, okay. So, but what happens in this loop? Capacitance was charging, and now it's discharging.